So far we learned about image classification pipeline, okay, and the BOW framework. So first part, it was composed of k-means clustering to make the histogram representation, and then we applied SVM, okay. And today we will learn about uh, the other stream of machine learning algorithm, which is called as linear regression. Okay. So this linear regression is called as linear regression because it has the linear representation and also it performs the regression. Okay. So you may remember what is the regression is. It is one of the supervised learning, but differently to the classification task, its output is having the continuous value. Okay. So anyways, we will learn about that. So this is the review for the machine learning algorithm. So given many X and Y pairs, the aim of the machine learning algorithm is to learn the function f, okay, which is also regarded as some machine. Okay. And regression, it is the one of the supervised learning. And given input x and y, if the y is continuous value, we call that as regression. Okay. Um, yeah, this is showing the difference between regression and classification. Both are supervised learning tasks, but the difference lies in the output space. Okay, if the output is continuous, then we call that as regression. But the output is having some discrete value, we call that as classification. That integer values in classification task means the class index. Okay, so we can map each integer to some of the semantic class, for example, dog, cat, and some other object classes. Okay, but in the regression, the y values itself has a semantic meaning. Okay, so for example, if X is the attendance score and Y is the the student's midterm score, I think there are strong correlation between this, midterm score and attendance score. Okay, so we can find this relationship between these values. Okay, so given these X values, finding the y values, that is called as a regression task. Okay, and linear regression, this is one of the simplest regression algorithm. Okay, so uh, I uh, I believe that you already learned about this linear equation. So in Korean, it's called as 1차 함수. So you may remember that linear equation looks like this. Okay, this is the linear equation in English. Okay, and in Korea, we this type of function is called as quadratic function, but in Korean, we call that as 2차 함수, or we can define many polynomials with n차 함수. So anyways, in English, we call this form as the linear equation, and we can call the other which have power. Power of x is larger than, if their power is larger than 2, then we call that as nonlinear equation. Okay. So linear regression is having the form as this. So that's why we call that as linear, linear regression. Okay. So in the linear regression, all the relationship between the input x and output y are having this linear equation. Okay, that's why we call this algorithm as linear regression. And this is the simplest form, actually, right? We can define many nonlinear equation to map input x to output y. Okay, but we are using the simplest linear equation to map x to the y, and that's called as linear regression. Okay. 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 So explain this linear regression in more detailed level, I will simplify more simple example. These values are not that simple. So I first set these x and y values more simple way. Okay. So x that is having 1 to 3 here, and when x is 1, then y is 1, okay? So actually, humans can easily find this type of y is equal to x equation, is the equation that can map input x to the y, okay? But the computer have to, have to have some algorithm find that the mapping between x and y are this equation. So I will explain you how we can obtain that, okay? So first, we are given this data, okay? 1, comma 1, 2, comma 2, 3, comma 3, okay? So we can represent those samples, 3 samples we are having in this 2D graph, okay? Are you guys following? Okay. And our aim is to find some straight line, okay? So the ground truth straight line might be y is equal to x, okay? But it is unknown to the computer yet. But we will anyways find this form of solution, okay? That can map these three, that can, best explain these 3 training samples, okay, that is happening during the training of this linear regression, okay. But depending on the A and B values, okay, we can vary this straight line, okay, we can vary this straight line. And these are close to these 3 samples, okay? But anyways, it is wrong hypothesis, okay? We have to efficiently remove this wrong hypothesis and have to find this orange straight line, okay? Anyways, we will formulate that because this is the linear regressor. We will formulate our formula that can map x to the y like this. So this could be a, but we normally call this as w, okay? And this is some scalar value, and this w is can actually have some. Uh, if x can have some value which is x can be some vector, okay? So which means there could be multiple element inside this x vector. So I mean, we when learn about this linear equation, we always think this x is some uh, having some floating value, but now we can also have some vector for x. Okay, so that's why we normally call this as the W. Okay, W can be some array. Okay, anyways, y is also 1 by 1 value. Okay, normally. Okay, this is, anyways, the formula that we usually use to map x to the y, okay? And b is also the scalar value. Um, I mean, this green line is randomly initialized uh, straight line, which means there are w and b in this equation. We first randomly initialize this w and b, okay? Then, that could be this kind of line anyways. And we will, anyways, define the error for these three training samples we are having, okay? Using this kind of formula, okay? So h of x, it means, sorry, h of x, it means this function, wx plus b, right? Okay, so if we input xi, which means the i's training sample to the h, okay, then then it will output something, okay, depending on their initial w and b parameter, it will output something, right? Okay, and that position, that y value is this one. Is that correct? Okay, so given the first x1, if we input it to h function, then their y value will be here, okay? Because this green line is meaning this function, okay? When we input x1, their y value is here, okay? But their ground truth lies here, okay? Right? Their values are y1, right? Are you guys following this? So their difference, this is meaning, how to say, this distance between this predicted value and also their ground truth, okay? And we normally use Euclidean distance to calculate this. So we, use the square here. And for the second sample, this is x2, and their ground truth is y2, okay? But their predicted value is h of x2, okay? And their difference is called as error, okay? And for the third sample, their, predicted value lies here, hx3 lies here, and the ground truth value lie here. And this would be their error, okay? So this red, the length of red means the error, okay? Anyways, we sum the error between predicted value using our function f, function h, and their ground truth, and sum over all the training sample, okay? And we also normalize that, okay? Average it, and that becomes error, okay? So when when our h is here, for three training samples, we can calculate our current error, okay? And then our aim is, given these two, for arbitrary h of x, we can calculate error, okay? And if we can get the w and b, which can minimize this error, and that will be the desired situation, right? Desired w and b values, okay? Is that correct? If we can find W and B that can minimize this error, okay, that best explains the training samples. That would be the proper W and B values, okay? And that can actually achieve this linear regression. So this is the linear equation. At the same time, it can explain the three samples regression, okay? Are you guys agree with this? Okay. And I mean, that will be this straight line, okay? But how to optimize it? How to optimize it? That is the question, right? We normally use the gradient descent algorithm for solving this type of, optimization, okay? Solving actually this type of uh, optimization, we use gradient descent algorithm, okay? But I mean, when our error function is very simple, like this, as you already seen here, it's in this graph, y-axis, it denotes the error, okay? Uh, I mean, for this equation, I will draw the 2D graph, okay? And there, y-axis is meaning the error, okay? And there, x-axis means this w, okay? And we can draw another graph for b and error, okay? So here, our function error is depending on two variables, w and b. So we can actually draw two types of graph, okay? But I mean, if you see the graph for this w, then this is the quadratic function for the w, okay? So its graph may have this form, right? And I believe you already learn how to get the global minima of this convex function, maybe from the calculus course, okay, by differentiating this function and finding the x point whose differentiation is equal to 0, that will be the global minima, right? So I mean, if your error function is very simple like this case, you do not have to use this gradient descent algorithm, but instead you can just calculate the point whose differentiation is equal to 0, okay? Then you can directly find where this error function has the minima, okay? Is that correct? But I mean, in reality, this error function is not that simple, but for the linear regression case, it is very simple. So, I mean, indeed, you can get the global minima of this linear regressor by differentiating this formula and finding the W directly. You can do that. But later, we will learn about more complex algorithm, and that their actually error functions are not like this. Okay, so for that, I will give you this type of algorithm. I will teach you this type of algorithm. Okay, so in that case, we have to iteratively calculate their global minima. Okay, so you can start from any W value. We will count W value first, okay? And then we will consider the B value later, okay? For the W value, its current value can be lie on any this x-axis, right? It can start from here or starting from here, depending on the random values, random initial values. You can start from any location. But let's assume you are now in here, okay? Then you will first calculate the differentiation of this error function on this point, okay? And then that would be like this, okay? I agree with this. If you calculate if you differentiate some arbitrary function and find the value for that point, that specific point, it means the slope of that function in that point. Okay? Are you agree with this? 이해되나요, 이거? 고등학교 때 배웠죠, 이거? 안 배웠나? 요새 바뀌었나요? 아무튼. 이거 미분하면 이런 펑션이 있을 때 미분해서 저 포인트에 대한 값을 구하면 그게 슬롭 경사 또 기울기 구할 수 있는 거 알죠? So here is the slope. Okay, slope of this function on this point can be found by differentiating this function and getting the value for this point. Okay, and you can actually using this slope. But I mean, originally this slope means how to say this direction. This is positive value. Slope of this is positive. Okay, but I mean we have to if we multiply minus value to this slope, and if we move our initial w value, I mean to the initial w value, if we how to say add this slope, then it can slightly move this direction. Okay, I agree with this. 누가 한숨을 쉬었 이해가 되나요? 네. And then in this next position, we can also calculate another slope at this point and multiply minus sign and move this parameter towards that direction, then the parameter will be W is anyways updated to this again. Okay. And again, it can reach the global minima. Okay. And at the global minima, the slope is 0. Okay. And anymore it doesn't move. Okay. And we can say it converges to the global minima. Okay. Are you guys following this? Okay. So I mean this type of algorithm is called as gradient descent algorithm. So we can formulate it like this. Okay. So this differentiation looks complicated, right? But it simply means the differentiation of error to the W. Okay. It means the slope here. Okay. And then we multiply minus sign on that. Okay. And also this epsilon is indicating very small value, like 0.001. Okay. And you are updating the previous times W to this direction. And then that becomes the new W, okay, at t plus 1 time. Okay. And you will iterate this formula again and again until your gradient goes to 0. Okay. And this is gradient descent, and the same thing will happen for the B value. Okay. And I mean, this is also meaning how your errors will be varied when you change your parameter W. Okay, it inversely means to I mean, how to say, if you multiply minus sign, then you can think this is meaning how your parameter W have to be changed to minimize your error. Okay, so this is some physical value that means where to go in the parameter space. Okay, and in that direction, you will multiply some small value, and then you will update your parameter in that direction continuously. Okay, and it will eventually stop at some point whose gradient is zero. Okay, right? I mean, sometimes it can stop in this kind of point. Okay, right? I mean, in how to say, uh, sometimes I mean, uh, I will explain this later. So you have to understand some other concepts for this. I will later explain about this. Okay. Anyways, this is the in practice, this works also for complex functions. Okay, not merely for this kind of quadratic function, but for other complex function, this this gradient descent algorithms, uh, I mean, works well. So we are using this to optimize uh, this type of formula. Okay. Okay. And for the case where your x is beta, uh, I mean, that kind of situation is frequently observed in machine learning problem. So let's say you are now having attendance score, but also have some quiz score and assignment score, okay? And your aim is to predict your midterm score using, I mean, quiz score, assignment score, and attendance score, okay? So your prediction might become, I mean, more precise than having only attendance score, right? So, I mean, this type of regression task is frequently observed in machine learning problems. Okay, we call that as multivariate linear regression because you are having multi-dimension for the input x, so they are called as multivariate. We can simply extend the variable x to the vector and can define w as array. Okay, and your h of x becomes like this, okay? But I mean, samely, this gradient descent algorithm can be applicable for this kind of extended multivariate cases, okay? You can simply use this gradient descent algorithm for these multivariate cases. And now we will learn how to implement this type of optimization, okay? So we now theoretically understand how this type of linear regression can be optimized, okay? But indeed, we have to implement this linear regressor in the code level, right? Okay. So for doing that, you can use two types of library, NumPy in Python or PyTorch. Okay. NumPy is, I mean, traditional library for implementing array in Python. So you can implement this linear regressor using NumPy library. Also, this PyTorch is developed by Meta, previously Facebook. Okay, especially PyTorch was introduced to implement deep architecture. Okay, but I mean, it can be also applied to this simple case. Okay. So in conclusion, I recommend to use this PyTorch to implement that kind of optimization problem. Okay. Because NumPy, you can do that, but that's not simple. Okay. You you have to consider, I mean, too much things to implement this type of algorithm. So you will see in subsequent examples. Okay. So this is the implementation of linear regression algorithm using NumPy library. Okay. Uh, I mean, some code are not updated. Sorry. 어, 혹시 자료에는 이거 혹시 매터리얼 다운로드 하신 분 있어요? PPT에 올라갔죠, 블랙보드에. 어. 여기 사인이 약간 다르지 않나요? 거기랑 잘못 올렸나? 어, 이게 마이너스여야 되고 이게 좀 부호가 바뀌어야 돼요. Anyways, here we will first make the data for linear regression. So this W and B is meaning the true W and true B. Okay. We will use W1 is equal to 1, W2 is equal to 2, W3 as 3, and B as 5. So we have this, but W is this having this value, and B has this 5 value. Okay, that's the ground truth for W and B. And we will also have the W and B, which is randomly initialized. We will actually update this W and B. Okay, this is randomly initialized value we will update. And then this X and Y, you randomly generate X value and multiply true W and adding true B, you can generate 100 X and Y samples. Okay, these are our training samples. Okay, and this gamma is meaning epsilon value, the small scalar value multiplied to the gradient descent algorithm. Okay. And this is empty array, which will accumulate rows for each iteration. Okay. And we will iterate through 100 iteration for gradient descent. So first, we will calculate the difference between predicted value. This is the predicted value. For X, we will multiply W and add B, which is random at initial iteration, right? We will find the difference to their ground truth. Okay, this is error. And for differentiation of error with respect to the W parameter, actually we have to calculate the closed form solution for that differentiation. Okay, so I mean, the error was defined like this. Okay, so the error, the W will be, say, Okay. Mm, mm. Okay, so this becomes here we are not actually squared. Okay. Uh, so here in this code, we are not squared, apply square for finding the error. Okay. So because I mean here errors are just the difference between y and their predicted value. So if we differentiate this error with respect to the w and uh, to say 이 코드가 okay. So I mean anyways uh, I have to maybe re confirm this code again. I think the code is updated from the previous material, but I mean this slide is having some wrong values. So I will re-amend that and re-explain this next class. But anyways, you have to calculate this differentiation by yourself, okay? D error dw and D error db using the formula you learned in the calculus, okay? And you have to find the closed form solution for this, how to say, this differentiation by yourself. You have to calculate this differentiation by yourself. And then you have to implement this part by yourself. W multiply some small scalar value and this gradient. You can update W, right? And you can update the B value using this DEDB, okay? And this is for accumulating your loss value, okay? Anyways, these two, to implement these two lines, you have to calculate this differentiation with your hand, okay? The closed form solution for this gradient have to be calculated and implemented in the code level, okay? Are you guys following this? And then if we do this using these iterations, and then print out the WB updated and the true W and B, then you can find the obtained W and true W is eventually become similar. Okay. This is the gradient descent. I mean, the linear regression that can be solvable using the gradient descent, using the NumPy library. Okay. Are you guys following this? Okay. 이해 안 되는 사람 있나요? 이해 안 되는 거. 왜 안 돼요? 어렵나요, 이거? 약간 이게 포뮬라가 약간 지금 착각이 이게 좀 이거는 이 부분은 다음 시간에 좀 명확해질 겁니다. 이게 지금 이렇게 실제로 요 식을 W에 대해서 미분해서 여기다가 적어줘야 되는데 뭔가 좀 잘못된 것 같아요. 제가 봤을 때. 좀 수정을 했었는데 매터리얼에 그 부분만 빼고 그 부분만 이해를 하면 돼요. 실제 그라디언트를 계산해서 여기다가 실제 요 부분을 구현을 해줘야 된다라는 거를 이해하면 되고. 네. But I mean, in PyTorch, uh, the implementation becomes a lot easier. I mean, because these parts are similar to previous. Okay, these parts are using the true W and true B, and we randomly initialize W and B and making the data X and Y, that's the same. And also we will initialize our gamma and some blank array for accumulating loss function. And this is the iteration for, we will do the gradient descent for 100 iterations. And in PyTorch, for every variable in PyTorch, you can see we initialize this W and B variable as the torch variable. Okay? In the torch variable, they are having two instance variable, W dot data, that is meaning their how to say actual value, okay, assigned. And this W dot grad means the gradient value, which means dE dW. E means error, okay, error. So if you differentiate the last error to that variable that is assigned to this W dot graph, okay. And also this is meaning this, okay. I mean, in the PyTorch, I will explain this part first. So if you, in the PyTorch, we define these four variables, W, B, X, and Y. Those are four variables we defined here, okay? And then using this line of code, we connect X, W by multiplying those two. And then we add B to get the Y, okay? And then we also connect Y print, this value, to the Y variable by calculating the error, okay? So inside the PyTorch, when you type this type of code, this is Y print, and also this loss, or we also call this as error. So inside the PyTorch, when you write this type of code, this type of internal graphs are constructed. So there are W, X, B, Y variable initialized as the torch variable, right? But here, we connect them using some operator. For example, we multiply W and X, okay? Which means we connect W and X value using the multiplication, okay? Sorry. We connect W and X by multiplication, okay? And we connect this value to B by adding them, okay? And also their intermediate output is Y print, but we do minus and doing the square for calculating the loss, okay? Are you guys following this? Okay. So when you write this type of code for every operation in the PyTorch, they are constructing this kind of internal graph. And now you can know which variables, how these different variables are connected via the operator to the final error, okay? And based on this graph, you can calculate these two gradient, d error, dw, and d error, db. Okay. So I will also show that how to do that in the later. I mean, in here, I will show you how they can calculate using this graph, how they update the final layers, the differentiation of final output respect to each variable. I will show you how they calculate that later. Okay. But anyways, uh, inside the PyTorch, they make this type of graph, but when we write this type of formula that can connect the variables, we defined as PyTorch variable, then this type of graphs are constructed. And when you call this low start backward, then these gradients are calculated. Okay. For every variable inside the graph, when you call this low start backward function, then they calculate differentiation of final layer, which means the loss respect to each variable, each variable lying on this initial graph. Okay, are you guys following this? That is happening when you call this low start backward. I will further explain about this later in this lecture. Okay, maybe spanning next lecture. Okay, and because all the gradients are calculated in their respective grad instance variable, you can now simply use their value. Okay. Are you guys understand this? So that grad variable it also have the data and grad. So to access their value itself, we have to access their data. Okay. And we multiply small scala and minus sign and update the W and B for 100 iterations. Okay. I mean, this is a merit of implementing this type of gradient descent using the PyTorch. So PyTorch automatically construct this type of graph inside. And by just calling this low start backward function, you can calculate this gradient without calculating their closed form solutions like this. Okay. So, I mean, finding this closed form solution is, how to say, time consuming, and you can also can make mistakes when calculating this. Okay. So it's not simple. Okay. But you have to do that when implement this optimization using the NumPy. But when you implement that using the PyTorch, you don't have to worry about calculating the gradient. Okay, that's the merit. Okay, this is already explained. And the results are same as the NumPy implementation. Okay. So, I mean, this is the difference between this part have to be updated. This have to be updated. I will amend this part, sorry. But anyways, the same can be implemented in PyTorch like this without calculating their gradient, okay, directly, explicitly. You can implement that using the PyTorch, just defining how they calculate the loss from the initial variables. From the initial variables, you can define how to calculate the final loss function. Then they automatically construct some graph structure I mentioned. And if you pull this loss step backward, then all the gradient, the differentiation of final loss respect to the initial variables are automatically calculated. So you don't have to worry anymore how to calculate the gradient. Okay. And then you can just use that. Okay. This is very helpful when you implement deep architectures, actually. So deep architectures, they are having many layers, okay? And there are many, many parameters. So if you implement that deep architectures using this NumPy, then the code required is very long, okay? But if you will feel that using this PyTorch, the implementation becomes a lot easier for complex deep architectures. Okay. Okay. So this is the graph I mentioned previously. So this type of graphs are internally generated, and you can make it easy. Okay. And I will explain you about more PyTorch-like code. Okay, so uh, previously we had to define this type of W and B parameters explicitly. Okay, but this is for defining this type of linear equation, right? Okay, so this is actually some function f we will learn. Okay, are you guys following this? Okay. Uh, but every linear functions are sharing this format. Okay, so in the PyTorch, we can just, uh, we can simplify this type of type definition, parameter definition by using this type of, how to say, code. Okay, so this torch dot nn dot linear is meaning we will make a function f that can map x to the y, but having the in features, which means the input dimension 3 and output dimension 1. Okay, and bias is true means we will use b. If you use false for this, then your function is just this. Okay. So for the same thing, instead of explicitly define their parameters themselves, you can make some network. Okay, we will now think this f function f as some network. Okay, network having three-dimensional input and one-dimensional output, and by having bias. Okay, this form, so this net becomes some function now, and inside this net, as the instance variable, it has W and B. Okay, that's the same thing, right? But for the implementation, if your function has many, many parameters, then, for example, it can have 10 lines of code. Okay, if your function, some network, have many parameters, this line of code can be even longer. Okay, but if you can simply define this function as this, how to say, torch function, then things are becoming very easy. Okay, because the function we are normally using for constituting this neural network is how to say, not varied. Okay, we normally use this type of polynomial or other types of polynomials are also not very complicated. So in the PyTorch, they are predefined this type of frequently usable, frequently used functions. Okay, and I mean, if there is no function predefined in the PyTorch, then you can also define your own torch functions. Okay, there is also, I mean, method for that as well. Okay, and instead of defining this forward function in this way, you can just input x to the network we define here, and then we can regard the output as y pred. Okay, and we can also make find the difference between these two. Okay, and for the implementation, I mean, this type of code have to be added. Okay. Also, uh, I will finish soon. Okay. We will do until here today. And also when we do this, we have to initialize the gradient values to known, which is similar to initializing your, I mean, when initializing this A variable, you assign 0 to that variable in C++, right? Similar to that, to prevent this variable is having some garbage value, you have to assign known value to gradient always, okay? And do calculate their forward, their output by inputting x to this and finding the loss, okay? And by applying this loss step backward, all the variables, we can find the gradient value, okay? And actually, you have to do this because when you call this, for each variable, W and B, new gradients are added to W.grad. They are not assigned, but they are appended to the previous gradient. So that's why you have to assign known. Okay. Okay. Anyways, but you can even make it simpler here. Okay. By defining optimizer. uh, in the PyTorch, we already defined the optimizer, which is the gradient descent, and other types of optimizer are, available. And we will also learn about which type of optimizer are there. Okay. But I mean, we will use the gradient descent as our optimizer. And for doing this, you may remember that this is gradient descent algorithm, okay? And the thing we need is this and this, and these are calculated by calling this loss start backward, okay? So when these two are pre-given, and after we call the loss start backward, we can calculate this new parameter W, okay? And for this optimizer, we have to give them these two pre-given variable. So this is the network's parameter. Okay, this is W and E. Okay, if there are more parameters for this network, then that will be anyways returned to here. Okay, and also your epsilon value have to be initialized. We call that as learning rate. So that's why they are called as LR here. But anyways, we assign gamma, which is small scale value, to here. Okay. So here, it means the original parameter, for example, this, and this gamma is assigned as the learning rate. Okay. And this optimizer is having that kind of information. Okay. And inside, for every iteration, you will assign known variable to each parameter's gradient. Okay. Instead, you can implement that using this type of code, one line of code. Unless using this, if your parameter have 10 types of variable, your lines of code for initializing this would be 10 line. Okay. To reduce that, PyTorch is providing simple function 0 underbar grad to initializing your gradient as 0. Okay. And also for this part, if you have 10 types of variable, W, B, and others, then this would become 10 line again. Okay. But they are in the same form. Their variables are added with their gradient value by multiplying minus and small learning rate and added. Okay. They are simple calculation, but consumes a lot of line if you have a lot of parameters. So optimizer that can deal with this reducing the line of code. Okay. So you can actually change this type of code to this type of code. Okay. The right side, it has more PyTorch-like code. They are doing the same thing. Their results are same, but this is making overall things a lot easier. Okay. And this is the last. Also, this is one of the error formula that can calculate the distance between your prediction and the ground truth y. Okay. They are implementing this type of Euclidean distance. But there are a lot of distance measure. For example, you can use just one norm, this distance between when calculating the distance between these two variable, right? Or other types of distance metrics are available. So in the PyTorch, we call that as loss, okay? And this Euclidean loss is already implemented as mean square error loss. Okay, this is another name for the Euclidean loss. Okay, so that's why we call that as MSE loss. Okay, and you can interpret this as some function. Okay, and using this function, instead of explicitly calculate this loss form, you can just input your predicted value and ground truth to this function. Okay, so this is how to say a lot more how to say easier form to implement in the code level. Okay, and to change the loss type, you can just change this function. Okay, loaded. Okay, and this is the final code we have now. Okay, and actually you will see later in this course, uh, this code repeatedly used for even complex deep architecture learning. Okay, so starting from the previous linear regression example, we slightly changed our training code like this. Okay, but you can feel that this is the linear network. Okay, which is very simple, but you can make this more complex and can define another net variable using a more complex architecture, right? Besides that, nothing is changed. Okay, you can exchange this net variable with more complicated network architecture, but nothing other is changed for training that network. Okay, so I mean, I'm explaining that this code is reusable for more complex architectures. Okay, and for the optimizer, you can involve other optimizers other than the gradient descent. There are more advanced optimizer like Adam and others, but you can just change this to Adam, okay, and can reuse other code, okay. I will also explain what is the merit of Adam and other optimizer compared to the gradient descent. Okay, there are some advantage, so we will learn about that later. And also to change the loss function, you can just change the name of the loss function here, okay? And you can reuse actually these 5 lines of code for more complex network and for other types of loss function and other types of optimizer, okay? This line of code will not be changed, okay? Okay, so, and then you will indeed learn this multi-layer perceptron in the Wednesday. And this is having the structure that stacks multiple linear layers. Okay, so you will see to get Y, this X is the initial X input. Okay, and you apply multiple linear equation on the original input X. Okay, so this is similar to stacking 3 layers of linear layer to the Y, to the X to get the Y. Okay, and if we define this structure as net variable and use the same code, okay, you can now you will see that network is also trainable using the same code. Okay, so that will be seen this week, Wednesday. Okay, okay. So this is end of lecture today. So see you this Wednesday. Thank you.